Alright, so here's an interesting physics problem for us. A model rocket blasts off and moves upward with an acceleration of 11 meters per second squared until it reaches a height of 30 meters, at which point its engine shuts off and it continues its flight in free fall. We're going to be asked a couple of questions, the first of which is what is the maximum height attained by the rocket? Now we know that it goes up to at least 30 meters, but it doesn't just stop and come right back down at that point. So here's my little doodle actually showing that. So we got our rocket, starts off here. At the very beginning, its velocity is going to be 0. During the engine phase, we'll call it, its acceleration is 11 meters per second. Its displacement is 30 meters. The one thing that they didn't tell us, but we can find, is what would the velocity be at the end of the engine phase. Now to find that, let's go ahead and look at the equations of motion that we're given. Now remember that time has not been mentioned at all in this question, at least not yet. So the equations with time, this one here, 2:7, this one here, 2:10, 2:11, those ones would not work, or at least wouldn't be very helpful for us right now. This one here, equation 2:9, this is the average velocity, and I'm sorry, the average velocity, which doesn't help me much because I don't have enough pieces for this. I only have the inertial velocity of 0. I either would need this one or this one, and this is the one I'm trying to solve for. So that leaves us with equation 212. So the final velocity is equal to, and they write it two different ways here. But the second half is the simplified version. So the square of the final velocity, I should say, is equal to the square of the initial velocity plus 2 times the acceleration times delta x. So in the engine phase here, I know that my initial velocity is just 0 because I hadn't moved yet at the very beginning of this. I know that the acceleration in this phase is 11 meters per second, and I know the displacement in this phase is 30 meters. So if I want to find the velocity, I'm going to have to find the square root of this to cancel that fella out. So let's find the velocity at the end of the engine phase. So it's the square root of 2 times 11 times 30. Okay, so we'll say 25.7. 5.7 meters per second. So at the end of this engine phase, once the engine shuts off, our velocity is 25.7 meters per second. But naturally, that's not what they wanted. That'd be too easy. They want to know the height of the rocket. So after the engine shuts off and it continues upward just a little bit more, how far does it go? Eventually, it'll reach a peak where its velocity will have to be 0. That's the point just before it begins its descent. So right here at this peak, the velocity would be 0. I can go ahead and I can reuse this equation. I'll use a different color, so hopefully it's a little less confusing. Let's use this color. I'm going to go ahead and reuse this equation, but this time I'm going to solve for the displacement. I have an initial velocity. At the beginning of this arc phase here, it's going 25.7 meters per second. At the end of the arc, it's going 0. I know that it's in free fall at this point. The engine is shut off, so its only influence is gravity. So I know my acceleration must be 9.81. So I can fill all that in to solve for displacement. So let's do that. So final velocity is 0. Initial velocity is the 25.7 meters per second squared plus 2 times, and then we've got our delta x that we're going to solve for. Oh, I almost forgot. That's what I was thinking of. So I just wanted to point out that in the textbook it does say that in all cases we're going to use for g the acceleration due to gravity is going to be 9.81. It's never going to be negative unless we choose a coordinate system with the positive direction upward, which we have in this one here. we've chosen positive direction has been upward. So I'm actually going to have to make sure I use a negative for that. Otherwise, I'll get the right number but the wrong sign, and that can be confusing. So just keep this section of the textbook in mind. Make a note of this. It might come in handy later. It comes in handy now. All right, so let's do some algebra and let's solve for this. So I'm going to have to subtract 0.7 squared, and then I'm going to have to divide by 2 negative 8.1. I put the parentheses in the wrong spot. Forgive me. It shouldn't really be there. There we go. That equals delta x. Let's figure out what the displacement is in this arc phase. So let's just go ahead and put this in. I had to subtract the velocity, which was squared in this equation, and then divide by 2, negative 9. Okay, so it looks like in this arc phase here, our displacement amount it moved is, let's say it's 33.7. 33.7. My initial displacement was given to me as, well, that's one significant figure, but let's round this to 2 decimal places just to keep it pretty balanced. So that would be 34. 34. So if we combine the displacement or the distance it traveled in the engine phase and the distance it traveled in the arc phase, we'll combine 30 and 34, and our total distance would be 30, 30 plus 34, which would give us 64 meters. That would be the height of the rocket's travel, so 64 meters. Okay, so the next thing they want to know, now that we know what the maximum height of the rocket is, I did say total distance, but you know, I should fix that. I should just say that's the maximum height. That's only really half the total distance. Anyways, now that we found the maximum height, we need to find part B. What is the speed of the rocket just before it hits the ground? So right here, what is its speed? Now remember that we've got symmetry here. We've got a parabolic shape. So right here, when it begins going straight down, more or less, the velocity rate at this point would have to match the velocity rate at this point, which we found was 25.7 meters per second. And we also know that this must be the same displacement as it was on the way up. It's going to be 30. Would be negative 30 now because it's going down. Let's go back and let's keep using this same formula. I've written and erased it too many times. Let me write it again a little bit neater. So the square of the final velocity is equal to the square of the initial velocity plus 2 times the acceleration times the displacement. And so in our case, it is the final velocity we're looking for. We're looking for right before it lands. So I don't know that. But I know my initial velocity, I can use right here, I can use the 25.7. 25.7. Now remember, it is in free fall, and because we chose up as positive, we're going to have to use our acceleration as negative 9.81. And our displacement, it is going down 30 meters. There's down 30. So let's go ahead and let's just plug this in and see what we get. I'm just going to make sure that I square root this whole thing in order to get just the velocity, not the velocity squared. So what do we get? I don't know, but we will. Okay, 25.7 squared plus 2 times negative 9.8. I'm sorry that part of my calculator shut off. I don't know, or cut off. I don't know how to make it fit the screen, but hold on. Okay, 35. So my velocity just when it hits the ground, just before it hits the ground, is 35 if I keep this at two significant figures. So 35 meters per second. Let's see. Why aren't you scrolling? Okay, there you go. 35 meters per second. So there's my velocity right before I hit the ground. So part C, finally, what is the total duration of the rocket's flight? Now there's a couple different ways that you can solve this one. I tend to overcomplicate things, and I think so does the textbook. So I'm just going to stick with the way the textbook does it. And we're going to break this into three different sections. We're going to find how long it took during the engine phase. We're going to find how long it took during the arc phase. And then we'll find how long it took during the descent. So we'll find 3 different times, and then we'll add them up to get the total. Okay, so let's find those 3 different times for those 3 different sections. Like I said, we're going to find the time for the engine portion. We are going to find the time for the arc portion. And then we're going to find the time for the descent. Do I know how to spell descent? Maybe. Okay, so we're going to find these 3 different times, and we are going to then add them up. You can see I brought back up on the screen here the different equations. Now we want to find time. We just need to make sure we pick an equation that we have enough info for. And I do think there are 2 of them that will work, but the book does use equation 210 here. And we can use it because we have our final distance, our final position, our initial position, our initial velocity, and our final velocity for each of these 3 different sections. So we can plug in all that information and then solve for t. And so that is what we are going to do. And it's probably going to be exactly as much fun as it sounds. So let's start with the engine one. So during the engine section, the final position was 30 meters. That was the end of the end of that. So 30 equals, now the initial position was just 0. It started at the ground. So plus 1/2. The final velocity we calculated way back when. The final velocity at the end of the engine phase was 25.7 meters per second. 25.7 meters per second. Oops, I meant to put the initial velocity first, but the initial velocity was just 0. Did I say that? I don't know, I'm getting tired. Either way, we only had one velocity that was 0, and then we'll have time right there. So if I'm going to go ahead and I'm going to solve this, let me see if I have room. All right, so what I'm going to do is I'm going to have to multiply the 30 by 2 to ditch the 1/2, and then I'm going to have to divide that result by 25.7 to isolate t. So first, 30 times 2. That's 60. That's easy enough to do in my head, even though I'm tired. But then I'm going to have to divide it by the 25.7. 25.7. Oops. 25.7. And I get 2.33. And for now, I'm going to keep a few of these decimals. It's usually a good idea to round at the end of a problem to express it with whatever significant figures you need at the end. Unless I tell you otherwise, I'm going to keep those. So it looks like the time it took during the engine phase was 2.3-ish seconds. So let's do the same thing for the arc phase. And we'll use that same formula. The formula calls for us to start with the final position. Now, the final position in the arc phase, we calculated over here, was its maximum height of 64. So 64. It started at 30, though. That was the initial position, plus the 1/2. And then if we want the initial velocity of the arc phase, remember, was right when it started, it was the 25.7. 5.7. I do have this first one backwards technically in the engine phase, but it is addition, so it doesn't matter which order you put it in. But back to the arc phase. So the initial velocity for the arc phase was 25.7, and then the final velocity for the arc phase was 0. That's where it reached its apex, where it kind of like temporarily stopped. And get t there. So I'm going to do the same process solving for t. This time I am going to have to first subtract 30 from 64, and then multiply that by 2, and then divide it by 25.7 in order to solve for t. So let's do that. So if I take the 64 and I first subtract the 30, and then I can multiply by 2 to get rid of the 1/2, and then I can divide by 25.7. Yay, stop doing that. 25.7. And I get that. 6, 4, 5, 9. I'm just going to write down what fits. In the long run, round off errors aren't that big of a deal for the class. In real life, that's a different story. But for the class, rounding slightly differently isn't really going to kill you that much. It's still good to try to do best practice if possible. I try. All right, so now the descent phase. So for the descent phase, its final position is on the ground. Its initial position was way at the top there at the 64, but it is moving down, let's not forget. So negative 64 plus the 1/2. I'm still following this formula here, equation 210. The final velocity during the descent phase, we found, where did we find it? It's over here somewhere. Did I lose it? All right, well, it was 35. I don't remember where I wrote it. Where did I write? I have no idea. Okay, doesn't matter. The final velocity was 35 meters per second. The initial velocity was 0 because remember the descent phase started right here at the apex when it was just for a split second stopped. And then I've got my t here. So for this one, what I'm going to have to do is I'm going to have to add 64 to 0. Then I'm going to multiply that by 2. Then I'm going to divide by 35. Hope I do this right. All right, so adding 64 to 0 is just going to get me 64. And then I got to do 64 times 2. That needs to be divided by 35. And I get that. 3.657142857. So these were the 3 different phases. It had the engine part, the arc part, and the descent part. You technically could break this up into 3 different parts than what we have here. There are multiple ways to solve this one, but this is how I decided to do it. And so to get the total time that the rocket spent in flight, I need to just add these 3 numbers up. So where'd my calculator go? All right. So 2.3346. I think I'm just gonna. Nah, I should keep them all. I said I should keep them all, so I will. 5 plus 2.6. What? I don't know how I'm doing that. 6, 4, 9, 4, and finally plus 3.6571428. Okay, I didn't even a little bit type that right, but whatever. Close enough. Okay, so if we add those all together, the total time in flight, doing that, would have to be 8.6 seconds if we want to express it as two significant figures. 8.6 seconds. And I believe that was the last question they wanted from us. Yeah, what is the total duration of the rocket's flight? 8.6 seconds. That is two significant figures. There we go.